So you arrive on site for a routine inspection at a solar, battery, or wind facility, and the plant is running well today, but during your review, you notice something concerning. The inverter manufacturer that supplied the plant stopped producing that model several years ago. The replacement control boards are becoming more and more difficult to find, and firmware support is limited. Lead times for the spare parts have grown from 2 weeks to 6 months. And this situation is all too common. It's called OEM, or the original equipment manufacturer obsolescence. And it's becoming one of the biggest long term operational risks to utility scale clean energy. What I'm going to cover today is what OEM obsolescence is, why it matters for modules, inverters, battery systems, how strong maintenance and spare part strategies can protect your site, and when refurbishment companies can help extend equipment. And lastly, what can be considered if you decide to repower the system. Understanding this is critical for technicians, managers, and asset owners that are responsible for the long-term plant performance. So first, OEM, you'll hear that a lot in the industry. It stands for the original equipment manufacturer. When a plant is built, the developer selects specific equipment. The solar modules, the inverters, the battery modules, the control systems, the protection devices, and the transformers or switchgear. Those products usually are manufactured for a limited period of time, and sometimes these manufacturers are releasing new models every couple of years. Not only do they shift makes and models, but the parts no longer are produced to support older models. Sometimes their support or oversight of existing equipment becomes reduced as they focus on new products, and the firmware updates either stop or reduce in frequency. And so replacement components disappear from the market, making operations that much more challenging. And in some cases, these OEMs not just change products or stop producing parts, but sometimes they leave the clean energy market altogether and cease to exist, which makes it even more challenging when it comes to determining what to do, either for spare parts, downed equipment, or replacements. This absence of support, absence of parts, or companies going out of business or not supporting the certain models or equipment that you have on site, this is equipment obsolescence. For utility scale plants, this is serious because they're designed to operate 25, 30, maybe 30 plus years. And that creates a serious challenge because inverters are often 7, 10, 15-year design life. Batteries may need augmentation within 8 to 12 years, and electronics like controllers and boards, well, these fail over time. Without planning for obsolescence, operators can find themselves unable to repair critical equipment, leading to long outages and lost revenue. So let's talk about why obsolescence matters based on each component. Well, solar modules degrade slowly over time, but the challenge is matching the replacements. So if a module fails 12 years after installation, the original model likely no longer exists. So replacement modules may have different voltage characteristics, power ratings, or even physical dimensions. And what this means is this affects the string voltage designs, maximum power point tracking for the inverters, and the mechanical mounting systems for these modules out in the field. Even a small electrical mismatch can reduce energy production across the full string. So for battery and energy storage sites, inverters are some of the most critical and complex components in the solar site or battery system. They contain the power electronics, the control boards, cooling systems, and protection logic. Now, these components are especially vulnerable to obsolescence because electronics have evolved especially quickly. Common issues are control boards that are no longer manufactured, cooling fans, assemblies, or cooling parts that are discontinued. So, an entire inverter block may remain offline. One of the biggest failure points is the IGBTs, or the insulated gate bipolar transistors, the main power conversion within the inverter. And so this conversion process, if that can't happen, the inverter simply can't operate and perform its function. That can mean several megawatts of lost production until a solution is identified. Now, battery energy storage is evolving quickly, and these systems face additional challenges, really with the chemistry evolution. Manufacturers are constantly improving the cell battery design, which means older modules eventually become unavailable. What happens then? Well, operators face incompatible battery modules, different voltage profiles, different thermal characteristics, different communication profiles, and it just makes to where this isn't just a simple, let's go replace a battery module. Now we have to re-engineer the system to accept new or replacement battery modules. Oftentimes, this is called augmentation. All right, so the first defense against obsolescence or equipment no longer being available or spare parts issues is really going to be strong maintenance programs. Good maintenance slows equipment degradation, extends the useful life, and allows for proactive identification of issues. For solar and battery sites, this is really going to include the thermal management. Heat is the enemy of our electronics, and they're out in the elements. It's really hot, it's really cold, there's huge temperature swings. So, regular maintenance on the cooling and the thermal management systems is going to be crucial for the life term of these projects. Cleaning inverter cooling systems, replacing air filters, inspecting fans and heat exchangers, and ensuring the proper airflow through our battery containers. This reduces the heat dramatically, which extends the life of our electronics. Another thing that typically causes failures is loose connections. Loose connections increase resistance and heat and potential arc fault events. Routine inspections include torque verification, infrared or thermal inspections, and just verifying the connectors and there's no signs of overheating, arcing, or issues with our connection points. These steps will prevent premature equipment failures. Another thing that comes into play is the dust, moisture, and corrosion, which accelerate equipment failure. Once again, this equipment is out in the elements, could be hot, could be cold, snow, rain, ice. Maintenance has to include inspections of the door seals, enclosure condition checks, making sure there's no signs of leakage or water intrusion, corrosion control, especially if it's around the coastlines or high corrosive environments, and environmental monitoring for these systems. The better the environment, the longer the equipment can live. Another preventive option that should be considered very early on is identification of critical components that could shut down production. Typical critical spares include control boards, power stacks or IGBT modules, cooling fans, communication cards, battery management system, or contactors. It's important to understand what are those critical components and to have the proper amount of spares based on your portfolio. When thinking about spare parts, you have to consider lead times, availability, and obsolescence. Some components take a couple of weeks to replace. Some components may take 6 to 12 months or even longer. So critical spare parts should be stored on site or regionally to make sure that you've got the right parts when you need them the most. Part of understanding our spare parts and our uptime or downtime for our equipment is going to be our mean time between failures. We should be tracking a failure history across our fleet based on technology, sites, or regions. If certain components fail more frequently, spare inventories should be adjusted to reflect that. Asset managers should identify when equipment will likely reach its end of life or certain failure points and prepare replacement strategies in advance. This could include repowering sites or replacing with newer technology. So in clean energy, when OEMs are no longer in business, OEM parts are no longer available, or lead times are too long, refurbishment companies play a critical role. These companies specialize in repairing and rebuilding components such as the control boards, the power electronics, the communications, and even the cooling systems. They may repair things like failed components, damaged electronic parts, and test original specification. The benefits to refurbishment is one, you already have the parts, you've already paid for them. It's reduction of waste. Number two, a lot of times this is lower cost than the full replacement. In many cases, it potentially has a faster turnaround time. And once again, for legacy systems, this can extend the life of the whole system. Now, when considering refurbishment, it's also important to understand the quality testing standards, what warranty support is available, and the compatibility with the site firmware and the controls. Not every component can be safely refurbished, so the engineering review is important. It's also important to note that whether it's automotive, electrical, aviation, a number of industries utilize refurbishment as a very common practice. At some point, repairing the old equipment may no longer be practical. That's when operators must consider repowering. Repowering means replacing a major system component while keeping the existing site infrastructure. So this could be replacing old modules with newer, higher efficiency modules, replacing outdated inverters with newer inverters, or replacing battery modules with the new chemistry or technology. Repowering has to have careful engineering and contractual evaluation to make sure that this would not create any engineering issues, performance issues, or contractual issues if those things were specified within the contract. Whenever we're changing, whether it's modules or batteries, we've really got to look at the engineering limits when it comes to voltage, the ratings, and the protection settings. Changes could affect the string voltages, the DC to AC ratios, and the inverter maximum power point tracking algorithm and ranges. On the mechanical side, new solar modules or battery modules may be heavier than the original. So engineers might have to look at different tracker structures, mounting systems, or foundations that can support the new equipment. Newer equipment may also have different protection settings, and so protection engineers must evaluate the relay coordination, the grounding systems, and the fault condition behaviors. In many interconnect or PPA agreements, there is a limit on plant capacity. So even if the newer equipment is more powerful or higher capacity, operators must ensure that the plant remains within the permitted export limits per those contracts. So when it comes to OEMs going out of business, parts not being available, or refurbishing parts, you'd always want to make sure to do a thorough review of your warranty agreements. Replacing equipment could impact warranties, service agreements, or performance guarantees. So it's always best to thoroughly review those warranty agreements prior to any full replacements. Now, let's be honest, OEM obsolescence is unavoidable in long-term energy assets. Solar sites, battery sites, if they're operating for decades and the electronic or equipment models are only produced for a couple of years, that means successful operators must plan ahead. They plan ahead by maintaining the equipment carefully, having strong maintenance plans, developing strong spare part strategies, and leveraging the refurbishment companies when possible. And lastly, they've got a plan for repowering when it's necessary and manage the contracts accordingly. Sites that get ahead of OEM obsolescence can extend plant life, reduce downtime, and protect the long-term revenue or asset return on investment. For technicians and operators in the field, understanding these challenges help ensure the systems that we build today continue delivering power for decades later.